This lecture is on work. I don't have a note guide for it, so you just have to write this on a separate sheet of paper. Work is equal to a change in energy. So we have a couple ways that we can write this. If we just write the formula, work equals delta E, we can see then that by expanding out where work is W, right? And E is energy. We can expand out delta E into EF minus EI. And we can kick EI over to the other side. And we can write this formula right here, which is the conservation of energy formula. With work. The reason this is important is because we'll use it later, but also because this shows that we always write work on the initial side. Okay, another way we can think about work is by multiplying two vectors. And what this says is that work is the dot product of the vectors force and distance. I know distance is technically a scalar, but here we're thinking of it as a vector. And so I guess it's more similar to displacement, even though we call it distance. All right, so when we do the dot product, which we also call the scalar product, we end up getting a scalar. And so when we do the math, it ends up looking like this. So what are we saying here? Well, what we're trying to say is that by doing this, work is a scalar. And by saying scalar, we're saying that work has magnitude. But does not point in three-dimensional space. So you couldn't say, for work, you couldn't say 200 joules north or east or something along those lines. And that's what separates it from a vector. Now, sorry about that. Where students get confused is that work still has a sign, right? And so work can be positive or negative. And what that means is that energy is gained or lost. So that positive and negative sign does not mean direction. So let's write that down. Gained or lost by what? We can say by the system. So did the energy was the energy gained by the system positive work? Was the energy lost by the system to the environment negative work? All right. So work has these signs, doesn't point in three-dimensional space. It would be nonsense to say a change in energy pointed east or something along those lines. And there was one more thing I wanted to add there. Or I thought there was. Oh, units. SI unit for work. Is joules. Or J. What is a joule? I have to think about that. So when I forget, I just write out one of my energy formulas. I plug in everything that I would normally have. And I see that a joule then is a kilogram meters squared per second squared. Now, another way to think of what a joule is would be if we just think about the formula work. Let's say W equals FD cosine of 0, we'll say. 0 is going to give us max positive work, which I'll talk about in a second. So cosine of 0 is just 1. So we get the max positive amount of work, which is W equals FD, which would have units of newtons times meters. So Newton meters are also, so we'll write another unit. So are also another way of expressing work, but we have to realize that Newton meters for work is not the same as Newton meters for torque. So that is confusing. And you might say, well, I wrote that little dot there. That little dot there doesn't have to be there. So Newton meters, definitely not the same as Newton meters for torque. And what we're saying there is that torque is rotational force. And torque is a vector. You know, if you remember, torque came from torque equals R cross F, came from a cross product. And a cross product produces a vector. So torque is in itself a vector, and therefore the formula ends up being RF sine theta. Max torque is done when theta is 90, when R and F are perpendicular. Max torque happens. It says when R is perpendicular to F. I know it's kind of hard to read. So I wanted to point this out because it can be confusing. But there you can see we have two ways to multiply vectors, right? One is the cross product, which is RF sine theta, mathematically speaking, and also happens, produces max torque when R and F are perpendicular. And then we have the dot product, which is what I want to talk about here. So work, I think I wrote it up here. Yeah, I wrote work is the dot product or scalar product. So I'm going to carry that on down here. So the way we write this, work is not a vector, right? So it doesn't get the vector hat, but F is and D is, and we write it like this. So instead of using the X in between the two vectors, we use the dot. So we call this the dot product or scalar product. And here, the formula mathematically, what this what this turns into is W equals force times distance times the cosine of theta. And max positive work notice I said positive work happens when F and D are parallel and point in the same direction. So max negative work happens similarly when F and D are parallel but point in opposite directions. So what I'm trying to say here, whoops, I got rid of some of my yellow square. Okay, what I'm trying to say here is that max positive work is going to happen then when theta is equal to 0 degrees. And max negative work when theta is equal to 180. And we should probably draw this, right, where theta is. We'll do that in a second. I'm just trying not to forget anything. There was something else I wanted to say here. Whereas that was different than torque, where max torque happened when theta was equal to 90 degrees, right? And so if we draw this, just very simply, theta is the angle between F and D. Notice we put F and D tail to tail. And that's similar to what we did for torque, right? Remember we always had R, and then we had maybe F out here, and they were tail to tail. And here was our axis of rotation. Oh, this is terrible. Okay, so we had something like that. So we're going to put F and D tail to tail. Theta is the smallest angle between. I mean, you could just think of theta as being the way it normally is, but this works better, I think. All right, so theta is the smallest angle between, and so we have this drawing here to go off of, where this is gonna work for us. All right, so let's draw a few things. I'm gonna move past this line here. So let's say, for instance, we have F, we have D, this dot here is my object, and these vectors are right on top of each other. They point in the same direction. So in this case, theta is equal to 0 degrees. I can't really draw it because the vectors are right on top of each other and the angle is 0, but you get the idea. So this is max positive work. Something that's worth knowing here is that positive work tends to speed objects up. I mean, the object's already moving in a direction, and all of a sudden we put a force on it further in that direction, so it should accelerate it and speed the object up even more. Let's look at another example. Let's say the force is directed up, but the object is moving to the right. In this case, theta is 90 degrees. And in this case, this is 0 work. Now, the reason it's 0 work, and this always confuses kids, is because I always ask them, when you get this situation, right, what type of energy is changing? Because they always think, well, if I'm holding something up in the air, right, if I'm carrying a box and it's heavy, or I'm walking with it at a constant speed, right, maybe I have a velocity this direction, it's constant. So I'm applying this force as I move in a distance this direction. What we're saying here, because that's 90 degrees, that this is 0 work, right? And if this doesn't make sense to you, well, what type of energy, right? What type of energy in this situation is changing? And you might say, well, potential energy. Well, that's not true, because the object, right, this box, its distance isn't moving up or down. Its distance is moving right. Kinetic energy. Well, that's not true, because V is constant. So you can see where this starts to make sense, that this situation right here, let me see if I can get a highlighter. This situation right here is a 0 work situation. All right. Let's get the so I would say 0 work tends to not change the speed. I say tends to because there's going to be an example on the way, I'm sure, where the rule doesn't apply, where positive work is being done, but the speed doesn't change. So yeah. All right. So then we have this case where we have the distance being directed right, but the force is to the left, right? And so this is going to be, our angle here is now going to be, let me see if I can draw it with orange. So this 90 degrees was orange. This time the angle is this right here, which is 180. And this is going to be negative work. Not only negative work, but max negative work. And this tends to slow objects down. Because think about it, the force is opposite the direction that the object is moving, right? So it should, this is like if you're sliding to the right, friction would be doing negative work since it points to the left. So tends to slow objects down. All right, so there we have it. 3 ways to draw these types of work. Okay, so you also have the situations where you have partial work being done, right? And so I want to point this out. So let's say F points this way, D points this way, or maybe D points this way and F points this way. And here you have theta or theta. You might say, well, I didn't draw the angle between there. You know what? If I would have, I think both of these drawings right here would have been the same. And so when you mathematically type this in your calculator and you take, say, the cosine of, let's say this is 60 degrees, and let's say the cosine of 30 degrees, they're, or 330, geez, 300. These are going to be the same. This is going to equal 0.5, and this is going to equal 0.5. All right, so anyways, we're going to get the same answer. So what I'm trying to say is this is partial positive work. And why is that? Well, if you think about it, work is done when, just like torque was only done by the component of the force that was perpendicular to R. So here we have our components of the force, right? We have Fy, Fx. Only one of these components does work. Which one? Well, last time it was the perpendicular component. This time it's going to be the parallel component. So what we're seeing is this force that's directed in the y direction does not accomplish any work. And that's where we're getting our formula from. Because think about this too. If you just think of this in terms of a right triangle, then we can see that Fx is an adjacent and F is the hypotenuse. Why am I bringing that up? Because cosine of theta is equal to adjacent over the hypotenuse, and we can say that the adjacent is equal to the hip cos the angle, and we can say that the adjacent then is equal to F cosine theta, right? And so let me write that again. We can say that Fx is equal to F cos theta. Well, all right. Well, if we keep with that, then, right? If work is Fd or F dot d, or work is force times distance, and we're saying we can only use the parallel force, right? Then we're saying here something along these lines, right? Just like we had F perp times d, now we have F parallel times d. And so what I'm trying to say is that we sub in Fx here from above, and we end up seeing that W is equal to F cosine theta times d, which if I just rewrite it, we get our formula for work. All right, so hopefully that makes sense, and you don't have to think that hard on it, truthfully. But I wanted to point out that this is partial positive work. When you use the formula, you have to use it correctly. What do I mean by that? Well, let's look at this. And I know I forgot up here to talk about partial negative work, but there is such a thing. What would that look like? Well, very similar to what we have over here. Here's our object. Here's our object. Here's our object. but instead of pointing 180, it maybe points like this. And another one being and another thing I want to point out, right, just like I did over there, is that the cosine of these two orange angles is equal. Now, I don't have an example here. These numbers are a little larger, but I don't know. Can I just think of one off the top of my head? 180 plus 30 is what, 210? Maybe this angle is 210 degrees. And then this angle would be, so what would be left there? 90 and 60, 150. So this angle would be 150. Whoops, shoot. So I'm saying, so what I'm saying here, and you can check it with your calculator, is that cosine of 150 is equal to the cosine of 210. All right, and you can check that out and see if that holds true, but it should be. All right, so this is partial negative work in this case. So, I don't like that. Let's see. All right, and let's also just underline this, make it a little cleaner and maybe easier to see. Okay, so coming down to when you actually use this formula in a practical manner on homework problems, it's super important that you do it correctly, because force and distance are vectors, right? But when you use this formula, you're gonna use just the, get rid of that, just the magnitude of this, so just the amount. So you're gonna ignore any signs. And just the magnitude of the distance, which shouldn't be hard because it's distance, but you get the idea. Even though these are both vectors, we're just using the magnitude. So your direction is all determined by the cosine of theta. So do you get a negative answer when you plug in the numbers? Do you get a positive answer when you plug them into the calculator? Because I'm guessing, and I do have my calculator in the other room. But if I go back to the partial negative work examples and I plug into my calculator cosine of 150, I get negative 0.866, which I think is the same as the negative square root 3 over 2. And if I do the same down here for 210, cosine 210, once again I'm in degrees, I did check it and it is correct. I get negative cosine, or negative square root 3 over 2, or negative 0.866, right? It's just approximately negative 0.866 because there's more numbers after that, right? So I think it's better to write square root 3 over 2. And I know your math teachers like that more. So coming down here, make sure you use magnitude, and let your cosine theta determine direction, and use degrees. We are not using radians. All right, good. Let's see, was there anything else I wanted to talk about here with work? I think we talked about just about everything. Those are my notes from earlier. Okay, so I think we're good. I think we should do some examples and then call it good there. But we got work as being change in energy, which is what it is. Writing it as conservation of energy. Work goes on the initial side. EI plus W equals EF. Work is the dot product or scalar product. W equals F dot vector D, which turns into this formula right here, which is the one we mathematically just showed below. Work is a scalar, has magnitude but doesn't point in three-dimensional space. Any sign on work shows up as positive or negative, which means energy lost or gained by the system. If it's a positive sign, the system gained energy. If it's a negative sign, the system lost energy. SI unit is joules. But you also can have this other sign, which is Newton meters, but do not confuse that with Newton meters for torque, because rotational force is different than a change in energy. They're completely unrelated, but exactly identical units, which is crazy. All right, and in SI units, a joule is a kilogram meters squared per second. If you forget that, write out your formula like I did right here, and then you can go through and just relearn it, because that's what I do. I don't memorize that. I ain't got time for that. And yeah, I got enough stuff to memorize. All right, and we can see that to draw work, I find that this drawing right here really helps to remember. Put the vectors tail to tail, and theta is the smallest angle between. And then that helps me on a lot of problems. Then you can think of the three types of work, positive, max positive, zero, and max negative down here, and how to draw them, tail to tail vectors in all cases. Notice the dot was right here, right here, right here. That's the same dot right here. And yeah. Partial work can also be done because only the component that is parallel does work. In these cases over here, we have the parallel component still being the f of x component, right? It's parallel to d, but it just points in the other direction. And f of y being the perpendicular component, not accomplishing work. That's just rough to see. So I'm going to write f over there. Let me see if I can clean this up. All right, something like that, right? And so once again, fx doing work, and we prove that with that little bit of math right there, looking at the cosine formula and understanding why if the parallel component does work and the parallel component is f cos theta, right, as fx is equal to f cos theta, then that makes sense then why w equals fd cosine theta for the dot product, right? If we're saying that the work is f dot d, and that's when the parallel part of the force is multiplied by the distance, we end up getting this, which is mathematically what we said at the beginning. And finally, when you use fd cos theta, magnitude, magnitude. Let your cosine theta determine the direction and use degrees. All right, let's do some examples. I'm going to pause it there for a second. All right, so let's look at on the end of the chapter of chapter 10. Let's go ahead and look at on page 312, problems 1 and 2. So problem number 1 says there's a 2 kilogram book lying on a 0.75 meter high table. Just go ahead and draw that really quick. Yeah, this will be my table. Okay, so here's the book. And kind of looks like a book. Anyways, you get the idea. So this book is lying on a table, and it says it's 2 kilogram. The book is 0.75 meters off the ground, because that's the height of the table. And it says if you pick up and place it on a bookshelf 2.3 meters above the ground. So here we have a bookshelf. See, I thought this line was going to straighten out for me, and it's not going to. And we'll say this is the shelf up here. And we're going to move the book up here. and this is 2.3 meters above the ground. During this process, how much work does gravity do on the book? So when we lift the book up, how many meters are we lifting it? Well, whatever this difference is right here, right? How much is that? Let's see. So that difference would be, we'll call it D for the distance here, is going to equal 2.3 meters minus 0.75 meters. And so what is that? 1.25, 1.55? All right, 1.55 meters. And how much work does gravity do? So if we draw a picture like we did up above, with our dot being in the center, and draw our force on there, which gravity obviously points down, and then draw our distance. Which, I can use a blue vector if you like. This is going to equal that 1.55 meters. All right. What is the force gravity? Let's see, I think it's Fg is mg. So that's going to be 2 times 9.81 or 19.62. And let's go ahead and write that down. All right, so what we're saying then is the work done by gravity, kind of running out of room a little bit, is equal to the force gravity times the distance, right? Times the cosine of theta. What's theta? Theta is this angle right here. I can use orange again if you like. So we see that theta is equal to 180 degrees. So down here then, we can go ahead and write this as work done by gravity is equal to 19.62 newtons times the distance, which is that 1.55 meters, times the cosine of 180. Cosine of 180, you should know that. That's just going to be -1. So then the work done by gravity is going to equal, let's see, this should be, if my math is right here, this should be 30.411 when we multiply it, but negative. And that's going to be in joules. All right. So, good. Now you could have said Newton meters too. -1, of course. All right. Next question. That was part A. Of question 1. Part B, how much work does your hand do on the book? Oops. All right, so for part B, let's go ahead and draw this. So once again, we got the book. How much work is our hand going to do? Well, person's hand is right here, under the book, and they're lifting it up. That's kind of a terrible hand, but you get the idea. And since they're lifting it up, the force from that hand, here's the dot, the force from that hand is going to point up. But we also know that the distance right, which we drew in blue last time at 1.55 meters, is also pointed up. Now, we can assume that the force of the hand is equal to the weight of the book. So this is going to be mg. So once again, that's going to be, so I guess what we're assuming here is it's lifted at a constant speed, right? It's just enough force supplied to lift the book upwards. And so if that's true, that it's mg, we have 2 kilograms times 9.81 again, which is that 19.62 newtons. All right, so this is going to be max positive work. So you can say W equals FD cosine theta. Theta here is going to equal 0 degrees. That's why I didn't draw the angle. And we can say this is the work done by the hand is equal to 19.62 newtons times that distance, which is 1.55 meters, times the cosine of 0, which is just going to be positive 1, right? Okay. So the work done by the hand is equal to a positive 30.411 joules, or Newton meters, whichever you prefer to write. All right, good. Yeah, so that's it for question 1. You can see pretty straightforward use of our W equals FD cosine theta. Notice we just wrote the magnitude for the force, and you can see that because force of gravity pointed down, we did not put a negative sign on there on 19.62 in part A. We kept it positive, so we just magnitude, and then let so magnitude for force and for distance, and then let the cosine of theta determine the direction. Okay, let's look at problem number 2. All right, problem 2 says we have the 2 ropes seen in problem 10.2 are used to lower a 255 kilogram piano exactly 5 meters from a 2nd-story window to the ground. Okay, so it's going to look something like this if I can reproduce this amazing drawing. Let's see. Oh, I shouldn't. Oh, this is going to be rough. Something like this. I don't know what this is supposed to be. Is this supposed to be like the pedal for the piano? I'm not sure. All right. Anyways, you get the idea. All right. I'm not going to waste more of my time drawing. Oh, and it's in the air, so there's no ground here. Just getting a little carried away with my drawing. Draw that pedal. There we go. Okay, so we have something like that. And we have 2 ropes holding this piano up. And they're at different angles. This first one is at an angle. Maybe I should do these in color, just so it's easier to talk about them. Oh no, I see. So we have tension. We have different names from T1, T2. I'm actually gonna draw the dot in the center of the piano first. Okay, so this blue tension, this is T2. And this is at an angle of 45 degrees to the horizontal. I'll just draw right there. So this yellow angle, we'll call that, I don't know, theta. Might have got a little carried away with the size of that theta. That's okay. We'll see how it goes. And then on the other side, we have maybe this purple vector, which is going to be directed like this. It looks like, yeah, it's a larger magnitude too. That's not within doubt. They tell us the values of T1 and T2. And this one is at a larger angle to the horizontal. And this is 60 degrees. I'll make this that bright green. We'll call this one, I don't know, we'll call it, I think alpha. Yeah, I think that's alpha. I'm gonna say alpha is equal to 60 degrees. All right, so we have those two angles there. Values for tension. Let's see, T1 is 1830 newtons, and T2 is 1295 newtons. All right, and then they tell us the weight of the piano. They give that to us, and that points straight down, and this is the largest vector yet. This one is 2500 newtons. They just call it capital W, which I'm not going to use because it looks so much like work, but I guess I can use it. They do put a vector sign over it, so maybe that's to differentiate it from work, so I'll keep it that way. But just to be clear, this is Fg, right? This is force gravity, and this is 2500 newtons. All right, so here's the deal, right? And then it says it's a 255 kilogram piano. I should probably write that down. We might need it. And they say it's being lowered 5 meters from a second story window, so about 16, 17 feet, right? 16 feet. And 17 feet probably. Okay, how much work is done by each of the three forces? Okay, so we know that D is going to be 5 meters, and it's going to point straight down. So let me go ahead and jot that in there. So this is D, and this is equal to 5 meters. All right, so, okay. Let's start with probably the easiest one, which, so we have to find the work of all these forces. Let's start with the force gravity or the weight. So the work done by, we'll call it work grav, is equal to Fd cosine theta, but in this case it's Fg times D times the cosine of theta. Now notice that the weight and the distance point in the same direction, so theta is 0. So we can say the work done by gravity then is equal to 2,500 newtons times 5 meters times the cosine of 0, which is just 1. 5 times 2,500, what would that be? Would that be 12,500, I think? Yeah. All right, and this is going to be a positive value here. So we're good there. Now it's going to get a little trickier, right, with these next two values. And we said that we have to use the angle between D and T1 and T2, right? So that shouldn't be hard. And I think we're going to be fine just doing that. So what are those angles? Well, in this case right here for the green vector, that angle right there would be 60 plus 90, or 150. So I'll just write that in as 150 degrees. I don't know if I should. Oh, wow. I did not want to. Okay. I'll just leave that there, that little mark there I was trying to make. So this angle, which I'm trying to shade a little differently or something so you can see it. All right, this angle right here is 150 degrees. And so this is our theta here for, we'll just call this theta 1. Okay, so theta 1 we're going to use to get the work done by T1. All right, so coming, let's see, let's get a little space here. So we're saying the work done by T1 is equal to, once again, what's our formula here? W equals FD cosine theta, right? I'm just going to go ahead and sub in what is relevant. So F is now T1, D is still D, and instead of cosine of theta, I have cosine of theta 1. All right, I can then say that the work done by T1 is equal to, T1 we said was 1830 newtons. Distance is 5 meters. And the angle I think we said was 150 degrees. All right, so we plug all of that in our calculator. We should get negative 7,924.13. Okay. So if we do that, then that's units there are going to be joules. And we're good there. Okay. And then now let's go ahead and do the same thing on the other side. So this angle here is going to be, this is this right here. Right, that angle. And so maybe I can add a little color there to clearly show you that. Let's use I don't know, orange. So what is this angle right here? Well, 45 plus 90, just 135. We'll call that theta 2. All right, so same way as last time, or pretty much the same method, but a little bit different. So once again, W equals FD cosine theta. That's our formula. W of T2 is equal to T2 times D times the cosine of theta 2. W of T2 is equal to, I think what did we say this was? 1295. All right. Times 5 meters times the cosine of, I think we said 45 and 90, 135. All right, so what is that mess right there? That's going to equal, let me see if I have that written down already. I think I do. Yeah, that's going to equal negative 4,578.52 joules. Okay. All right, and wouldn't you know it, I bet if we add those two together, let me do that real quick in my calculator. 7924.13 plus 4578.52. Obviously they're both negative. It's gonna, if we add them together, we get 12,502.65. So what I'm trying to say is that is the exact opposite of the work done by gravity, right? And gravity did that positive work, that 12,500, and the two tension values are going to do negative 12,500 because the piano isn't speeding up. It's moving down at a constant speed, and therefore we see this balancing out. Okay, another way you could have did it, which I just want to point out because, all right, so I had to stop it there for a second. The other way you could do it was if you take, let's see, if you take the piano, I'm not sure how, if I'm drawing this right, yeah, okay, and I draw it one more time. I think we had T2, which I think we made blue, right? Pointed at 45. and we had T1, which we said was purple. We had it pointed at 60 degrees to the horizontal. Not sure what color I gave those. Was it green, yellow? Okay. So let me label this. So if we look at just T2, right, and just want to calculate this work, for instance, in a different way than we did before, we had force gravity obviously pointed like this, or weight, or whatever you want to call it. But what I want to show you is it's all about the parallel component, right? So I could have used an angle. I could have used a different angle than what I did. So let's look at this blue vector here. And let's split it into a perpendicular component, or an x component, which we'll call T2x, and a parallel component to D, which we will call T2y. And this puts our puts a 90-degree angle right between the two. So my point here is that if we knew T2y, we could get the work done by T2y, because what we're saying, right, with T2 is that T2y is the only part, like, I didn't draw distance, and I think I drew distance in red, didn't I? Yeah, and it was the 5 meters. Okay, so let me get rid of that. So I'm saying this. Here you have D equal to 5 meters. And since only the parallel component does work, what I'm saying here is T2x isn't going to do anything, and T2y is going to do all the work. So we can just draw just the important part, which is T2y, which I don't know why I'm making it so large, but I am. Okay, just about right there. And I'll label it. And use this angle instead, right? What the heck is this angle right here? Well, we know that, right? That is orange here. This is 180 degrees, right? So I can label that theta equals 180 degrees. But what is T2y? Do we know T2y? We have to come over here and get that. T2y is an opposite. T2 we know, which is, I think, 1295, yeah. And this is our hip. So we just use something with op and hip, which is sine. Our hypotenuse was 1295. So we can see that T2y is going to equal 1295 newtons times sine 45. So long story short, then, we can now find the work done by T2y, which is equal to the work done by T2, is what I'm saying. The work done by T2y, and that's kind of what I want to show you. That's my main point, right? That work T2y is equal to the work T2, because only the parallel part of T2 does work. So what would that equal? That would equal whatever this mess is right here, 1295 sine 45. I have to go get my calculator. Times, I didn't write it out, all of it. W equals FD cosine theta. That's okay. All right. So there's F. D is going to be 5 meters. And then theta is going to be that 180 degrees, right? So that's what I'm trying to say here. So I'm using this formula right here. That W T2y is equal to T2y times D times the cosine of theta. And theta is at 180 degrees. So, let's go ahead and write that in. So we have over here, I need to crunch this in my calculator. Give me 1 second to go snag that. There's moving rooms here. 1295 times sine 45 is 915.703 roughly newtons, and then cosine of 180 is just going to be -1, so -1 times 5 is -5 meters. So we multiply those two and we get -4,578.52 Newton meters or joules. Whoops. My eraser is set up too large, because whenever I erase, yeah, it's like erasing like multiple things, and I don't want it doing that. All right, so my point here by doing this, right, is not just making this problem longer, is that this is the work done by T2. And if we go back up and look, -4,578.52 joules, that was what we got up here for work done by T2. All right, so only the parallel component does work, is what the point of showing you that second way of just looking at T2, the work done by T2. So the whole problem was, of course, to find the work done by each force, which happened to balance out because the piano was moving at a constant speed. All right, that's it. So hopefully this is making sense. And yeah, and that's all. So have a good day.